All right, so now let's get started looking at these line integrals. So we're going to be dealing with some vector value functions, some work we had kind of introduced back in chapter 13, creating those functions R of t, those vector value functions. We have that parameter t most commonly. And so a way of identifying some curve is whether it be a parabola, a circle, right? A straight line even. We have some path, some curve we're going to follow that we can locate in space by this R of t vector value function. And now we're going to evaluate an integral along that curve. Okay, so let's start to discuss that action and that operation. All right, so for our line integrals, this idea, let's kind of start off with this concept, this overall idea, and then we'll start to break it down into these components. We can, of course, work in 3 dimensions as well, but let's start off with our 2D, R2 first, right? But we're going to be able to expand on this, go to 3 dimensions, hopefully fairly quickly, right? It just entails a longer integral we have to deal with. But this concept, okay? So this idea is that if we have some curve C, right? So this is our curve or our path that we're following in space. And again, it could be some polynomial curve. It could be parameterized. That's what we're going to start to see. Most likely, this parameterization, okay? But now what we're going to talk about is that we're going to want to integrate over that path C some function. We'll start off with our xy, right? Because depending where we are on that path, we have some function acting on that curve. And what we're going to use is this ds component. Okay. But this is our line integral. What we're kind of doing, we're integrating this function f of xy along that path C, okay? And what we're kind of doing is that we're computing along segments of arc length, and that's what that ds component is, right? Because what this concept is that we have this short little span of ds, and we can, again, think of those components, all these little segments of arc length building up from the start all the way through till the end of our curve, okay? Taking those little segments, adding up what our function is doing over that segment, okay? And 3-dimensionally, right, what we kind of identify, this is like finding that kind of area under that curve along this path, right? And so even though it is a 2-dimensional function, right? That's like our z coordinate, our height, right? We have our curve C here. Sorry. There's our curve C, that R of t. And above that curve, we have our function, whatever it might be doing. So this is in 3 dimensions, this is our f of xy. So above this point, we could plug xy in, and it's going to give us my z coordinate. Above this point, plug it in, we get our f of xy, the z coordinate, so on down the strip. And so then as we start to take these little components of ds, we're multiplying, again, that function's height times the ds, right? So we're getting this little strip of area. It's only calculating one side. So the way I've heard it discussed before, I think in the textbook even, is like if we have this fence that's going up along like this hill of our property, and we want to compute, okay, how much surface area, how much paint am I going to need to paint my side of the fence, right? That's what this is computing. It's getting our height times the width, and we're just summing those up along our length here, along our curve. Okay. So that's what we're kind of visualizing. That's this overall idea that we're conveying. Okay. And so as we start to go through, if we looked at just simply integral, if our function is a constant 1, this is just the arc length of how long that curve is. Okay. And so back in our second semester calculus here at MPC, you might remember with some of the arc length discussions there. Okay. This is going to be equal to this integral over c. Okay. Of this arc length, the s here, dx dt squared plus dy dt squared dt then, right? Where we can parameterize c as that kind of function. R of t is x of t I plus y of t j. So every location, we can get the x and y coordinate based on time. Okay. We're identifying any point on that curve as that x of t, y of t. The r points from the origin to that point is giving us that location vector pointing wherever we are. So as long as we have our x of t, y of t, we can differentiate and get those components. And so then we can integrate from a to b of that component. Right, where c is that portion of the vector function r of t from t equals a to t equals b, right? So between this interval is going to produce that curve. Okay, and so again, this is a little bit of drawback from our Calc 2 discussion, getting that arc length for these parameterized functions. Okay. And then, so for our line integrals now, when we're integrating over C, that function f of xy ds, we can reorganize this as rewriting this integral from a to b. Our function f of x of t, y of t, right? Replacing x and y with this parameterized form in terms of t. And then for that ds, that arc length, dx dt squared plus dy dt squared dt, right? Again, C is that portion of R of t, which is x of t, y of t for t between A and B. So as long as we can parameterize, that's for a little bit of work we had done back in chapter 13. I know it was brief, by starting to get those functions in terms of parameter t for those curves. A big problem we do is like kind of doing a half a circle, that semicircle, where x is going to be cosine t, y sine of t, right? Even if we do like a parabola, if it's the curve y equals x squared, let x equal t, y is going to be t squared, or that x squared. Just kind of building up those equations for that curve we're following. And then we're just summing up that product of our function parameterizing t times that bit of arc length. Okay. And so that's where the work's going to come in, parameterizing. Okay. And so as we go in, let me do this note. Okay. If needed, we can also separate our path C into smaller segments. Okay. So for instance, if we're integrating over C, our function f of x, y, and our curve C is something like this, where maybe we have like starting here, this line going upwards, but then it starts to turn into a parabola, half a circle, whatever it is, right? So in this case, if this is our path C, what we can do is that, well, maybe instead we can start to separate the way we parameterize. I can parameterize this line segment first, and the way we find that arc length along that line, that calculation might be a little bit different than for this segment of our curve, which is maybe like this parabola or some other function, cosine curve, sine curve, so on, right? But just the way we can separate our regions with our double integrals before, we can separate these curves over which we're integrating, these paths that we're following. It's still the same function acting on that curve, but the way we compute, the way we parameterize may be different, right? And again, we might have these bounds on T that could be totally different, or, right, kind of their own defined for that curve. So rather than calling it CD, which of course we can, it might be the case that this goes from 0 to 1. This also goes from like 0 to 2. Something as simple as that. It's just how we define, how we parameterize that portion of our curve. Okay. And then that computation, that DS, again, just goes back to how we create that parameterization for that curve based on that R of T. Okay. And then this applies as well to 3 dimensions. Okay. And so if we have, in this case, our curve C, again, kind of like thinking about it, if we have this kind of helix, where depending on how much time has gone by, we're just following that loop. We would want to integrate our function adding up along that way. And again, maybe the physical meaning is a little bit more difficult for us to identify or state quickly, okay? But in that same discussion, we still have this notion that, okay, we're taking our function and letting it act on what I say, right? It's multiplying, it's acting on this little segment of arc length, working our way through that curve, whatever it's doing in 3D space. And then as we continue, as long as we can parameterize that curve, have some kind of R function, some bounds on T, if we need to separate into multiple points, multiple parts, we can. But now we're going to have our function parameterized, X of T, Y of T, Z of T. And now for that arc length, we just have to expand into 3 dimensions there. Sorry for being a little bit short there, but just expanding 3 dimensions in that same version. Okay, so I'm just setting up these integral statements first, okay? Then we'll get into our calculations. Set up with some of these, all right? One last component that I want to deal with, that I want to manage, especially with these kind of 3D versions, is that maybe that we're going to be integrating through a vector field, right? We have that magnetic field, that magnetic force field pushing along this electrically charged particle traveling through, and we wanted to kind of capture, or kind of sum up all those forces felt by that particle, accumulate that, the total force that it feels, or the total charge that is accumulating, right, as we work through that space. Okay, and so here in this discussion, these line integrals through vector fields, and again, this could be 2D, 3D, okay, or integrating along some path, but now we're going to have some vector field function dotted with this dr. Okay, so again, this is going to be vector field fxy or xyz. Since we're dealing with vectors now, this is going to be a dot product. And now this piece, this dr, this is our little segment of that vector curve, right, where C was that R of t. So it's just like the ds, now we're calling dr because this is vector value function, okay? More in line with what we're managing. Okay. And so what we kind of see with this integral as long as we can parameterize that curve between A and B, we have our vector value function, evaluate it all these different points along our curve, dotting with this r prime, so taking that d, right, the derivative of r dt. Okay, and maybe off to the side here. dr, if we do d dt of the r of t, right, that's going to be dr dt, whatever that derivative component-wise looks like, multiplying both sides by that segment dt, that's kind of where, right, multiplying both sides by that dt, how we're getting that dr component to be that expression. Okay, and then we can see this as a kind of a tangent curve, r prime, right, our tangent to that space curve r of t, and we can look at those components as well. Okay, but I think this is like a big way that I manage these calculations. And so once more, what this is kind of thinking about is that if we have this kind of vector field working in our three-dimensional space, and again, I know it gets a little bit awkward to draw here, all these little arrows, my little vectors here, right? Little forces felt. And if we have some curve traveling through, we're just kind of imagining taking these little segments and acting on that little segment of our curve with that vector field F. Right? Acts on, pushes on segments of that curve, RT, which is C, okay? And we're kind of accumulating, adding those up with that integral. So the big segment, the big discussion that we're going to end up having is how are we going to be able to create those R of T, those functions to parameterize our curve here, okay? How are we going to build those components? And then just substituting in to that formula for our line integral, okay? And that's where we can kind of go back to some of the discussion. I'll put some of those notes back up from the textbook as well for that parameterization of our curves from chapter 13 in conjunction with this information, okay? And I can write up some examples to share, but there's our introduction to these line integrals.